I'm Phil Jones. I've been playing bass for over 50 years and designing audio gear for about 40 years. And I'm at home right now because of COVID. Can't work in my office or lab. But I want to talk to you about PJB, Phil Jones bass amplifiers, and why we have small speakers. In the past, when I started off, I used to think like everyone, big speakers are better, why? Because they play louder, they got more bass, and that's the way it was. But with technology moved on, things have changed a lot, and I'm going to tell you the story why that is right now. I learned electronics in University of Cardiff, and also as a bass player. I loved playing bass. I grew up in Wales, Cardiff, Wales. Grew up with Pino Palladino, who's a friend of mine. We played in the same circle of musicians, which I could now, but that's another story. And I went to music college and I studied classical double bass because in Wales back then they didn't even consider a bass guitar to be a proper instrument. They said you have to learn a double bass. I went, okay, I want to learn music theory, learn double bass. And I was playing around with bands. I started learning to play upright as well, and playing with a lot of jazz ensembles and rock bands and disco bands, because that was the time, back in the 70s. And playing bass, I was never happy with my sound. I went through tons of gear. I had Fender, dual Showmans, acoustic 370s, put JBL horns on top to get the snap, and I was never really happy. And also I met a guy who was a cinema sound engineer, and he gave me lessons in sound, and I realized I knew nothing. I was dumb. And I got an interest in designing audio gear. I did a 10-year, maybe 9-year stint of doing live sound reinforcement in London, working with some fairly big bands, and a big PA system I owned and operated. And what happened was I started getting very tired of doing concert sound. It's a very stressful job, a very tiring, very high energy job. And I bought a house in London and set up a recording studio, a 24-track studio. And in that studio, I started building near-field monitors because I wasn't happy with the sound of my near fields. I had big JBL 4333s, which were a great speaker of the day. And I wanted to have a very similar kind of dynamic response and frequency response in a small speaker. There were nothing existed. So I built some near-field monitors. I learned how to build drivers, and I made my first speaker units back then, And in that time, I started a company called Acoustic Energy, the AE1, which was a pretty successful speaker. I then went to Wharfedale and became chief designer at Wharfedale Speakers in England. And I got fed up with the damp weather over there, and I immigrated to the United States. First, I was offered a job with JBL, and then I was offered a job with Boston Acoustics, and I went to New England and worked with them, designed the Linfield series, left Boston Acoustics to start my own company again, which was Platinum Audio, and we built a whole range of little speakers. I used to use 5-inch drivers because it's a perfect speaker size for good bass and mid-range in one unit. And at that point, I was asked to build like a statement piece of audio gear. And my Japanese distributor said, I want something very special for Japan, and there's no price limit on it, no physical size, nothing, just build whatever you can. And I came up with a horn-loaded 360-degree sound field speaker called the Air Pulse. And that won the Golden Sound Award in Japan. And it was a very hefty price tag. I mean, retail was $250,000, for one pair, which is ridiculous. But, there's people out there that got more money than God, and they got to spend it on something. So we sold 11 of them, 11 pairs. Platinum Audio had some partner problems, and also I saw the writing on the wall that things were happening in China, and I decided to move to China. I lived in China for 5.5 years, setting up another company called AAD, which is Air Pulse and Phil Jones Bass. And in 2002, I said, I really want to make bass amps because it's my passion. And at the time, I was married to my first wife, and she couldn't stand me buying another bass guitar, and I could buy another bass guitar and call it Research. So that's why I ended up with I got 80 basses, by the way. So that's way too many for anybody, So the next thing was PJB started off, but at the same time, it was carried through with my home audio business, which we partnered with a company called Edifier, which are a huge company in China, and I became a designer for Edifier as well. And now we have Air Pulse and Phil Jones bass, and some of the Edifier design as well. And we have a huge factory. I mean, the factory is 1.2 million square feet, and we have an incredible research facility. We have a huge anechoic chamber. It's maybe good down to 40 hertz. It's one of the biggest anechoic chambers in the world. And we even have a Klippel laser Doppler interferometer. It's a great piece of German technology. And that tells you the ugliness of your work. If you get it wrong, it'll clearly show up just how bad it is. And it does scanning of the speaker, and you can see it move in 3D. Microscopic levels of how the behavior of the cone is, the suspension systems. And these days, anybody's a serious speaker manufacturer's got to have one. If you don't have that, you're not in the business of manufacturing drive units. That's my opinion, anyway. So that's basically my history up to now. What makes a good speaker? Well, first of all, a good speaker is one that's designed for the application it's going to be used for, right? You could say that like a little Bluetooth speaker is a good speaker if it's, you can put it in your pocket and you can take it out camping or something, A good bass guitar speaker has a different application. What you're looking for a bass guitar is, in my opinion, would be like, number one, it handles the spectrum of the instrument. So it doesn't have to have like a super tweeter, but it can go like, it doesn't have to have a subwoofer. It has to go down to a certain frequency that makes it feel good. And it has to have the power to generate what you need to keep up with the band and fill the hole. And the other thing it's got to be is portable. There's no point making a speaker the size of a small car. It's got great sound and you can't move it about. I guess you could put big wheels on an engine on it and drive it to the gig, So, growing up with that and learning about live sound, live acoustic sound, and then live electric sound, I got into home stereo. I always like to have a good sound system at home, and the first thing I did was I went out, and a friend of mine who was a sound engineer, said that they were shutting down a big cinema in Cardiff for the Capitol Theatre, and they were throwing out the speakers in the dumpster. So I went round with a big van and picked them up, and I stuck them in my house. And my mum came around the next day and saw these giant monoliths, they're like 7 feet tall in each corner. And she said, "What the hell are those?" I said, "They're speakers." And she called a psychiatrist the next day because she said, "I was completely nuts about sound." I probably am, but I said, "Mum, you got to know what Stanley Clark on it. It's just killer, But the whole town could hear it. It was that loud, And and I was running it with like 50 watts a channel because speakers were so efficient back then. Those big tube amps, KD88 on each side, Leak CL50 pluses, and so I love that big dynamic sound. The downside is it takes up half your living space. And so when I was standing in a recording studio and founding Acoustic Energy, I said, can I get that massive sound in a tiny little cabinet? What's the engineering challenges I got to do it? It's a bit like, if you like automobiles, like the first V8 was like some German guy, like 1924 or something, the first V8 came out, 3.2 litre, and it was like 24 horsepower. If you had a 24 horsepower car today, you'd be, I suppose, a golf cart, not a car, So, today you can get a 2 litre engine, 300 horsepower. So the same goes with speakers, that the power's gone up and up and up and up and up. And, if you look at the reason why, if you take like an old Goodman's 18-inch, it was back in the 1960s, had a handling of 50 watts, and today you can buy a professional audio 18-inch and take 1,000 watt, and you go, wow, it's 20 times more powerful. Is it 20 times louder? Not really. They just run hotter because in the old days, the speakers were all held together like horse glue and all kinds of, organic compounds. And by the time they got to 200 degrees Fahrenheit, they go up in smoke, and that's why they couldn't take the power. So, with the advancement of DuPont making Kapton as a voice coil former, which takes like about 800 degrees F, and high temperature enamel wire, I can't remember the F, 250 degrees C it can go up to, and high temperature epoxy adhesives, we were able to make a speaker take a lot more heat. And you got to remember that a speaker is actually more efficient making heat than it is sound. Most speakers about 1% efficient sound, 99% goes to heat. So it's vital that you maintain the ability to withstand the heat in a speaker. And what happens is that when you have a hot running speaker, high power speaker, like you got a 400 watts on a 15 or something, the voice coil is getting up to 240, 250 degrees C before it blows. And as it gives a rise to a thing called power compression in a speaker. That's the reason for that is the wire in the speaker itself is getting hot. And there's a physical constant of a conductor, whether it's aluminum, copper, silver, whatever you use in a voice coil. Mostly copper, because copper is silver's too expensive. Aluminum is difficult to kind of solder, and copper is just right. So it has a temperature resistant coefficient of like 0.49% increase in resistance for every degree centigrade. So consequently, you end up with a speaker that may be at room temperature, which is like, they say, being English, I think in metric units more than I do imperial, 20 degrees C, and then the speaker is taking no power, room temperature 20 degrees C. It can swing up to 220, and when that happens, the resistance element in the voice coil can go from 8 ohms cold to 16 ohms, almost 16 ohms hot. And so when you're playing loud, you haven't got an 8 ohm speaker anymore, you got a 16 ohm speaker, and the current limits, and when that happens, you get power compression. The other thing is with the new advancement in neodymium speakers, and we use a lot of neodymium in our speakers. Highest grade, which we use N52 in our speakers, the strongest neodymium available, and it has a great property of being super strong and light. It's 25 times stronger than an equivalent ferrite ring magnet. However, the temperature rise is 1.1% or something degree rise temperature every centigrade. It loses 1.1% degree of flux. So they end up with a hotter speaker with a higher impedance coil and a weaker magnet. So the speaker is changing around, and when you're playing, you got to remember that like a CD player or some kind of machine doesn't hear itself. A bass player or any kind of musician is responsive to the sound that's coming back, the feedback, like a biological feedback loop. Comes into your ear here, goes to the brain, goes to your hands, play the instrument, goes back to the speaker, comes back to the brain, and it's kind of going around like that. So anything you do playing here and it's not right there, you subconsciously trying to correct it, and that can be fatiguing, using a lot of processing power in your brain and things. So what you really want is to have an immediate, non-latent signal, and it's accurate in dynamics, every bit you want, without having to compensate, playing that way. Like an acoustic instrument, like a piano, you play a piano, it doesn't have any variation, it plays everything. But and the other thing, when you play away with a big amp, you move away from it, say 20, 30 feet away, you're getting a time delay. You're getting like 20 millisecond, 30 millisecond time delay. So it's never exactly what you're playing. There's this opinion, people think that a certain size speaker has a certain tone. I prefer a 10-inch over a 15-inch. I prefer, 12-inch or something. But you got to think about it in a more realistic way. It's like, what it's not the size of the cone, it's like what goes on behind the speaker. There are things in cone dimensions that change. One is the physical size of the speaker like this, and the physical size of wavelength causes, what's the word, dispersion changes in the sound. You know, like the bigger the speaker, the more it's going to beam at the upper mids and higher frequencies than a smaller speaker. And but then there's the cone material, there's the size, the choice of magnet, the topology of the magnet, you know, the enclosure itself, what's the enclosure made out of, you know, all these things contribute to the sound. And you got to remember one thing about a bass speaker is, if you think ordinary speakers like guitar speakers are not that efficient, bass speakers are even worse. I mean, there's a reason for that. And one of the reasons is that you have to have movement in it. As you go down in low frequency, every time you half the frequency, you double the excursion. So it's a bit like a guitar string. You see a guitar string, you know, it hardly vibrates on the upper, like you play E string on 12th fret. It doesn't go like a bass string where it's like that. And there's a relationship between velocity and of the string and the frequency. So if you played at a certain level, the velocity of the string, whether it's an E string or A string, doesn't change. It's just going backwards and forwards more at a higher frequency. But if you had a greater amplitude, then the velocity increases. So that's so, you know, going back to, like, again, the speaker design, you got to understand why speakers are inefficient. You know, I'm changing things around here because I'm just ad-libbing this. When you have a sound wave, the speed of sound is extremely fast. You know, like 767 miles per hour on dry air at sea level, for example. That's pretty damn fast. You know, we can't even make cars that go that fast. Planes go that fast, but, you know, not any commercial planes anymore these days. And if you take a look at a loudspeaker, you know, the cone is moving at a very, very slow speed. In fact, if you calculate like a calculator, if you had a maximum output of a speaker, and it would be like a big, massive car subwoofer, it's moving like that much, at 40, 30 hertz, it equates to like no more than like walking pace, like 4, 5 miles an hour, maybe 6, 7 kilometers per hour. So you've got this disparity of the movement of the cone, very slow speed, the velocity of the wave, very high speed. And that is what they call an impedance mismatch, an acoustical impedance mismatch. That's why horns are developed. Horns were developed to increase efficiency of a loudspeaker by, like a gearbox is to an engine. Like if you've got a bicycle and you want to pedal fast, you want to get out of low gear and put it in a high gear, so you're pedaling like that, but the wheels are going much faster. And a horn does that. It kind of transforms the high pressure, low velocity of the cone to the low pressure, high velocity of the sound wave. Like a speaker, like as efficient as they are, it's a bit like having a bulldozer pushing around feathers. I mean, there's just such a disproportionate amount of load on the cone to what they should be, you know, because of air is so light, you know, and therefore you need, it doesn't bite the air like it should. That's why big speakers have got better coupling to low frequencies than small speakers. And so when you're talking about a bass speaker, you know, it may be like, you know, this big, you know, like that. That is tiny in relation to the fundamentals of the wave. You know, a typical, like an E string's like about 36 feet long, you know, 3 meters, or 3.2 meters or something long. Is that right? 10 meters long, not 3. I'm thinking out loud. And you got this tiny cabinet producing these massive waves. So what happens with the low frequencies is they become omnidirectional. They don't beam. Like the upper frequencies beam like car headlamps, and the low frequencies just go everywhere. So when you're on stage with a bass cab, a lot of energy is going backwards as well as forward. Not the mids, but the low basses, and that's what you hear. You know, your ears are very critical in music. You're really looking at like maybe 300 hertz to like about 4 or 5 kilohertz is where all the information is. You know, if you have a telephone, for example, that has that kind of response, like, you know, a cell phone has no bass, but you can still hear everything going on, because if you had a bass guitar and you just took away all the harmonics and just had the fundamentals, you would hardly hear it. It would be drowned out in the mix. You have to have those mid-range harmonics penetrating through to get you kind of musicality. So the low frequency is going to kind of go backwards and sidewards and upwards and everything, and that is why with bass it's very inefficient, and it goes, and that's why it changes from venue to venue, and you go outside and then you got no bass because it's going upwards instead of being contained by a ceiling. So when you have boundaries like a wall, a floor, two sidewalls, a corner like that, you're containing the wave to go forward, and that's why you get a lot more bottom end out of a speaker. In my line of bass amps, if I have any favorite speaker, more than likely it's probably the C9. It's our latest generation of drivers. It's an old cabinet design. It's one of our earliest cabinet designs. The reason why I like that cabinet is it's still fairly compact. You can move it around easily. And as a bass player, I really like low-end bass. I mean, all my audio systems at home, go down to like almost DC, like very low bass. I like a lot of low bass synth as well, like 25 hertz rumbling bass. And the C9 cabinet can do that. And how it does it is, I got to talk about what it is. The size of the cabinet is minute compared to like what's out there, compared to other stage gear. You can barely put a 15-inch speaker in the baffle of that cabinet. It will just about fit in there. And you've got 9 5-inch drivers, which is kind of like equivalent area to a 15-inch speaker. If you added the carrier of this cone, the area of this, and the area of this, and all of them together, and then you looked at the surface area of the cones, it's similar to a 15-inch driver. The difference is that if you had a really high quality, great 15-inch professional grade speaker, you're probably talking about a 4-inch voice coil and power handling maybe 400 watts. You can basically say 1 inch can take 100, 2-inch voice coil can take 200, and a 4-inch will take 400 watts, because you're increasing the size of a coil, and what determines the power of a speaker is the temperature. You get to that ceiling limit 250 and it's done. It's gone in smoke. So apart from the bottom mount of farting out when you're hitting the low frequency, cone excursion is mechanical. Very often that will sound bad, but it doesn't always destroy the speaker. But burning out the coil, you're done. You have a recon job on it or in the trash. This is my simple question. People ask me, say, well, what about like ohms and impedance and matching amp? And I go, the best thing is buy a combo. If you buy a combo, you just have to plug it in the wall, plug your bass in, and EQ it, and away you go. A lot of bass players do it the hard way. They buy this speaker and this amp, and they're mismatching things. They're not exactly unless you're really a good audio engineer, you won't really understand what you're doing. For example, you can have mismatched impedances on the speaker, mismatched power, because one speaker is taking more power than the other speaker because of mismatched impedance. The amplifier as well. Now, when you talk about 4-ohm speaker, 8-ohm speaker, that's strictly not true. That's actually the minimum impedance at one point, but a speaker impedance is all over the place. You could have a 4-ohm speaker, could go up to like 100 ohms, at resonant frequency of the cone or at the other end. And the reason is there's 4 stages of impedance of a speaker. Because it's a moving thing, and when you've got a moving cone, you got electrical, you got mechanical, and you got acoustical parameters all interplaying together. So when anything acoustical is changing, it goes back and changes electrical parameters. And what will happen is if you look at the cone, how it's moving, it's basically like a weight on a spring. So if you had like a spring with a weight, you pulled it down, it oscillate up and down like that. That happens in a speaker cone. At a small scale, you've got a big heavy cone and a suspension like a spring, and it moves like that. And so what you have initially is the inductiveness of the spring. Like a spring is like kind of inductive in nature, mechanical nature. So from like low frequency, like to 20 hertz or 10 hertz up to the resonant point, the impedance rises, and then you kick in the weight of the cone, the capacitiveness, the storage of energy in the cone, which is like a capacitor. And then you at the peak you have the resonance. And then the impedance falls down maybe at about maybe 120, 150, 200 hertz, and then it stays level for a period of time up to maybe 500 hertz or more. And that is the DC resistance of the coil, because there you've got no cone excursion and you're just relying on the resistance of the coil. And that is the most damaging frequency a speaker can handle, because the current is at maximum, the cone excursion is at minimum, which allows some air cooling as the cone is moving back and forwards. It pumps air in and out of the voice coil gap. And the impedances are in phase. With electrical AC theory, you have to take power is volts times amps multiplied by the cosine of the phase angle of the relationship between the two. At the point of minimum impedance, just above cone resonance, you've got almost like a zero phase between voltage and current. So the true power to the speaker is almost the same as apparent power, and that's the maximum power the speaker's going to take. You can't really hear it, and you can burn it out at that point. Then above that, you've got the parasitic inductance of a coil, and that causes a rise in impedance, and that's why like long coil, big heavy speakers roll off faster than others. That's one thing. Another thing with a speaker is there's a thing called mid-range modulation that I worked on when I was at Boston Acoustics, and what happens is when you have a coil in a magnet, it takes the ion around the coil and increases the inductance of the coil. So when the coil moves outwards, let's say it's sitting at like maybe 0.3 millihenry, which is like typical of a speaker, moves out, it might go to 0.15, 0.1 millihenry, because it's leaving the magnet ion behind in the coil. But when it goes down the other way, it could go to maybe like 0.45, 0.5 millihenry. So you have this switching of modulation of inductance, and that actually can alter the mid-range. You can modulate the mid-range at high excursion levels. That's why if you had like a car subwoofer and you put full range music on, the bass is going, you can hear the modulation in the mid-range. They used to call it Doppler distortion. You can't hear that. It's mid-range amplitude modulation caused by the parasitic variation in the voice coil inductance. So I believe that if you want to go looking forward in development, you've got to look at the history of sound. And the history of sound started off with I guess commercial sound, the cinema, big, massive, super efficient loudspeakers, low wattage amplifiers, and over time it's turned around to becoming smaller, lower cost, easier to make speakers with less efficiency, because we got gobs of power with D-class or pulse width modulation amps. We make an 800 watt amp that weighs 5 pounds, and it's a true 800 watts RMS. So with that kind of power, does it really matter if the speaker's that a little less inefficient? I would say no, because what matters is you got a certain box a certain size. Let's say ideal would be like a 1 cubic foot box that could fill an auditorium, but it might take gobs of power, but that's the way things are going. Speakers have become, efficiency means big. You got a pie chart. If you have a pie chart like this and you've got 3 sections in that pie chart, every section, if you move one, it takes off one of the other sections, off of the 2. So you've got physical size. That's one slice of pie. The other is efficiency. How loud do you want it? And the other is how much bass do you want? So any of those parameters, more bass, less bass, how loud or how inefficient you want it, or that's what the other one was, physical size, So a big, super efficient speaker can have gobs of bass, and the downside is it's just huge, super efficient. But if you're looking for something, a balance, something small, then you have to sacrifice the efficiency, because you don't want to give up the bass. You want the bass there, and you want, So you take off the efficiency and you take off the size. Size is going to be all the way down. So efficiency comes to part. Then you got to put more power in. Can it take the power? So when we designed our speakers working at lower voice coil temperatures, because there's so much coil area and wider bandwidth too, by the way, you've got these parameters that you're looking for. So the ideal bass amp would be something that's like super loud, super small, and great studio sound quality and affordable. And the other thing is that if you don't want to get involved in understanding technology, we make a series of combo amps where everything is tailored. The wattage, the impedance, everything is all matched, and the EQ for that cabinet. So, we like the Road Case is one example, or the BG400. They're dedicated, very specifically tuned all throughout. We don't have to question anything or how to balance it out. So I think the future of bass is going to be, one day maybe we can make a thing the size of a wallet, but you have to have like 1 million watts of power to get any bass. I don't know. I mean, there's a practical limit where you can go, but right now I think PJB is at that forefront edge where we are, and the reason is we do a ton of research. We've got incredible facility to do all the manufacturing. We have incredibly big 3D printing machines. We can look at vent velocity. We calculate the air. By the way, going back, a vented speaker cone moves at 4 miles an hour. The air vent velocity can move at 70 miles an hour, but the sound wave coming out is 767 miles an hour. So that's always the downside. Your inefficiency of speakers is always going to be there, and even the most efficient speakers ever made were like 10 to 20%. There were some that were 50, but they were like the very beginning because they had to do that because of the limitation of amplifier wattage. Nowadays, with affordable, high power amplifiers, what you're concerned about is the ergonomics of getting it around, storing it, carrying it, and is it loud enough to do the gig. I don't believe in how many watts that matter. I think what matters more than anything is how many dBs it can put out and what's the response of the speaker. Can it play a low bass? Can it play the great clean mids? Can it play the highs? And how big is it? Don't care about the watts. The watts is nothing. That's like something that you can't hear watts, but you can hear decibels. That's what matters.